Threonine is one of the 20 amino acids that's used to make a protein within the human body. Now, just like every other amino acid, there's going to be a center carbon, the chiral carbon, the central carbon, the alpha carbon, the stereocenter. The carbon that's in the center that has 4 different attachments. One of the attachments is going to be a carboxylic acid group, where you've got a carbon double bound to an oxygen, also bound to an oxygen attached to a hydrogen. Another is going to be this amino group, where you have a nitrogen that's bound to 3 hydrogens attached to the center carbon. This nitrogen should only have 3 total attachments, and so because it has this extra hydrogen bound to it, this is going to carry a +1 charge. And then it's also going to have a hydrogen directly attached to the center carbon. And then the thing that makes every amino acid different is the R group. Now, at its lowest pH, the fully protonated form, or the form where everywhere you can have hydrogen, you're going to have a hydrogen, that's what the threonine is going to look like. But as you increase the pH, some of these hydrogens are going to have to be lost into the environment, because the environment is going to have fewer hydrogens than the molecule, so it has to balance things out. The first hydrogen that's going to be lost from threonine is going to come from this carboxylic acid, and that's going to happen at a pH of about 2.1. So this oxygen is going to lose that extra hydrogen, it's going to gain back its lone pair, and now this oxygen is going to carry a -1 charge. This amino group is still carrying a +1 charge here, so we've got a -1 and a +1 that overall balance out to 0. But because these do have individual actual charges, this is called a zwitterion. Now, as you keep going up, increasing the pH, aka losing more hydrogen from the system, so this molecule is going to have more hydrogen than the system is. The other hydrogen is going to have to be lost from this nitrogen, and it's also going to gain back its lone pair of electrons. When this nitrogen gains back its lone pair, it's now neutrally charged. This oxygen is still going to carry a -1 charge. So overall, this is going to carry a -1 charge. And this nitrogen is going to lose its hydrogen at a pH of about 9.1. However, at the physiologic pH, or the pH that is in the human body, aka about 7.4, that hydrogen is still going to be attached to this nitrogen, but the hydrogen is going to be gone from this oxygen. So the zwitterionic form, where it's overall 0 charge, but there are actual formal charges on the molecule, the zwitterionic form is what's going to predominate in the human body. Now let's talk about its R group. Now this R group just has 2 carbons. One of these carbons is going to have an OH group, which is known as an alcohol, and then it's also just going to be a CH3. So this OH group is able to do hydrogen bonding, and because it's able to do hydrogen bonding, this is considered a hydrophilic molecule. The way that it does the hydrogen bonding is because this carbon to oxygen and this oxygen to hydrogen, those are both polar bonds. So there's going to be moments where it's going to have more electrons with the oxygen than with the carbon or with the hydrogen. And at that point, it's able to bond to other hydrogens or oxygens or nitrogens or other molecules that are able to do hydrogen bonding, because they also have polar bonds. Threonine is not a molecule that is made in the human body. You have to eat threonine in your diet in order for it to show up in your proteins. So threonine is an essential amino acid.